Hello, welcome to this video. Now this is going to be the first one on the series on general relativity, and in this video we'll be looking at why discussing general relativity, and therefore discussing how gravity comes into the picture, requires that we deal with a curved space-time, and what we mean exactly by a curved space-time. Well, I say exactly, we could be getting a good physical intuition. We'll go into more mathematical rigour as we go through this playlist. But on the note of mathematical rigour, if you saw this video pop up on your recommendations and were thinking, oh my god, a video on general relativity, what has YouTube done? Is this going to dissolve into a sea of Greek letters? Well, in a sense, yeah. In a sense, I apologise to say, but we are going to be dealing with a lot of Greek letters. However, my goal in this playlist, as with a lot of videos on my channel, is to make or provide physical intuition for the mathematics. So we're going to be doing a lot of maths, but we won't be, focused heavily on making it completely mathematically rigorous. What we'll be trying to do is interpret the maths and understand, the story that the maths is trying to tell us. And in this story, we're going to start with kind of this video, where we introduce what relativity is, and therefore see how gravity and the curvature of space-time are, in truth, really one and the same thing. And then from there, we're going to, start considering how we generalise special relativity to start to talk about curvature, and then develop the mathematical tools for describing curvature generally, and before applying it particularly to an understanding of gravity. And then we can talk about really cool and exotic objects like black holes, or other more theoretical constructs in space-time which really emerged from studying well-known phenomena like black holes. And these kind of objects are things like wormholes, which kind of can connect one event in space-time to another, or even to otherwise separate structures of space-time, separate manifolds of space-time, if you like, so separate universes. We also will probably talk a little bit about white holes as well, because there's been a little bit of research done on them. And whereas wormholes were designed to create a more pleasingly aesthetic solution to black holes, because black holes, as they were presented by black hole as they were presented by Schwarzschild, had a singularity at the centre, and a wormhole is just a way to get around the idea of a singularity by implying that it actually opens up before it reaches a point of infinite density, so we get that kind of throat-like structure to a wormhole. Whereas a white hole was essentially going, well, Einstein's equations, as seemingly are, I think, pretty much all the fundamental equations of physics, are time reversible. So, if there's a solution in one direction of time, then there will also be a corresponding solution where we just reverse that direction of time. And a time-reversed black hole is a white hole. And then we might look at the possible connections between pairs of black holes and white holes and wormholes. So, we'll be going to some interesting places, and we'll also have a little look at cosmology and dark energy. We might look at dark matter. It depends, because nobody's quite sure what dark matter is, so whether it's something that concerns general relativity beyond it just being a matter, is not at all necessarily clear. But we will definitely have a look at cosmology in the latter part of this playlist. So that's what we've got coming up here. And if you would like to be notified when other videos come up, maybe kind of like hit the like button or hit the bell icon to let you know when more videos will be coming up on this playlist or on this channel generally. And if you would like to check out Special Relativity, I've got a playlist on this channel as well. Now, you don't need to be an expert in special relativity for this playlist, but I will borrow occasionally ideas from it. But anyway, I'll talk about material that might be good to use along with this playlist at the end to help one get the most out of learning about general relativity. But let's get cracking with the first bit of our journey together into the world of curved space-time and gravity. So we need to start with understanding what relativity really is, so that when we're talking about general relativity, we know the kind of principles we're trying to work with. And it's particularly helpful for those of you who may not have seen special relativity before to have a bit of a think about what relativity means, which will help make it clearer the structure we have to go through to generalise special relativity. Well, relativity essentially comes from the fact that there's no special time or special notion of position in space. All these things are relative. For example, I might say, how old are you? And you might say, I'm just making up an age. Well, there is an age range of people who are watching these videos, but let's just say it's something like 20. So you might go, well, you're 20 years old, but if I ask you how old are you, I might have meant how old are you relative to the birth of the sun, in which case you would be about 5 billion years old. If we take t equals 0 to be when the sun started to be the main sequence star, so time is a relative concept. Also, physicists, and I can say this because I myself do this practice, are, we're rather, physicists tend to be slightly egotistical. So when we're saying, the time at which something happened, we tend to mean the time from whatever we're calling the present. For example, if let's try to find an object that I can drop safely. So probably not my Lord of the Rings mug, but let's take this cardboard lid. So I might go at what time does this lid go out the frame of the camera? And I will probably take the time t equals 0 to be the time when I release the lid. But I could have taken the time I released the lid to be t equals 1, or t equals 2, or t equals 5,551. So I'll get lots of different answers for the time that the lid fell out of the frame, based on the fact that I can have lots of different answers for when the lid began even being in the frame. So time and space are relative. Where my laptop is, relative to me, as I'm making this video, may be completely different to where my laptop is relative to you. And that relativeness mattered. I mean, for example, like, we use the relativeness of space at least all the time when we're using maps and stuff. For example, if I wanted to help you find, the laptop I'm using to make this video on, I could say, well, the laptop is about 30 centimetres from me. So I might say the laptop is 30 centimetres, say, along the y-axis. And that's a valid statement. But if you're all the way in, for example, Australia, you really want to know, okay, well, if the laptop is, say, 30 centimetres from Jamie, how far and in what direction is the laptop relative to yourself? Because it's not going to be 30 centimetres from you if you're in Australia. So whenever people are trying to meet across the globe, or whenever there is people are moving from one location to another, and you've got people coming from different directions, how you map the description of where something is in time and space from one observer to another observer is absolutely critical and important. And it's that relative notion of time and space that actually has physical meaning. For example, if you're all the way in, for example, Australia, I'm based in the UK, so if we were going to meet at a particular point, let's say France, to do that we would have to take account, for example, if we were looking at directions, we have to take account of the fact that the Earth is curved. So relative motion can tell you about things like curvature, at least relative motion over a sufficiently large region. So the relativeness of time and space is what has meaning. The individual components we give to any event in time or space from the perspective of a single observer, like where my laptop is in time and space according to me, is not a very useful concept. But how we jump from my description of where the laptop is in time and space to yours, that is actually a physically important thing that actually has physical meaning. So relativity is about getting to those transformations. And in the context of space-time, we call a point in space-time, so something that occurs at a point in space at a single instant in time, we call that an event. So space-time is made up of lots of smoothly connected events, and the way you describe a point in space-time is by giving that point components based upon a coordinate system. And in physics, we call a coordinate system, we call it a reference frame. So relativity is the study of essentially how different observers would perceive the same event in space-time, but in their own unique reference frames. Equally, you could say relativity is about how to transform the components of an event from one person's reference frame to another person's reference frame. So how to go from where my laptop is according to me in space-time to where my laptop is according to you space-time, for example. Now, relativity doesn't have to actually make use of either special or general relativity. You can have more classical notions of relativity, and in fact, you've used classical notions of relativity all the time before. And it's useful to consider this before we look at special and general relativity, to understand the kind of chain of logic and reasoning that allows us to physically and mathematically have a strong understanding of the transformations from one reference frame to another. Or in other words, to understand the structure that any theory of relativity would have to have for it to make mathematical and physical sense. So let's take a nice classical example. So here I've kind of sketched out on my iPad a cartoon scene. My drawing isn't great, so unfortunately a lot of the objects I draw could be either balls or cubes, but we'll have to just deal with that. And I consider that this ball is flying upwards, so it's got some velocity upwards, but there is a downwards gravitational acceleration. And I've drawn two images of it, one to the left and one to the right. So the one to the left, we've got the velocity is positive and the acceleration is negative. And on the other image, I've said the velocity is negative and the acceleration is positive. But it turns out that both these sketches are correct, or at least they are both equivalent. They're referring to the exact same thing. There is no physical way to say that one is correct over the other. And to get from the image on the left to the image on the right, we can think that we've essentially flipped our notion of basis vectors. So essentially what is defining up or down along the vertical axis. So, we've made v from plus 4 meters per second to minus 4 meters per second, because we flipped the unit vector that is referring to, up, if you like. And when we flip these unit or basis vectors in the vertical axis, what's conserved, that is actually keeping the physics the same and making the two sketches essentially equivalent to each other, is that the acceleration and velocity are pointing in opposite directions, and also the size of acceleration and the size of velocity is the same. And if you look at the Seebeck equations, you can convince yourself that providing we keep the relative directions and the magnitudes of our acceleration and velocity vectors the same, then the equations of motion agree entirely and become equivalent for both our sketches, so the one to the left and the one to the right. And the reason why our Seebeck equations end up providing the same answers, for example, if I was considering how long it would take for the ball to reach its maximum height, the reason why we get the same answer for both sketches and why the physics is the same for both sketches is there is no physical law in place that is saying what direction up is or what direction down is. So I should be able to flip my basis vectors that are saying what is up and what is down. That is, I should be able to turn up to down and down to up. And providing I do that consistently, I should be describing the exact same physical scenario, and the equations of motion shouldn't be any different. And the idea of there being no standard up or down, is also then leads to things like the question of, well, if a ball falls to the earth, is the ball accelerating to the earth or is the earth accelerating to the ball? And that is actually a question we'll look at more carefully when we look at kind of things like geodesics and stuff in general relativity. But the main point with relativity is relativity is about jumping from one reference frame to another, whilst keeping things preserved in accordance with some physical principle that says that, you know, both reference frames should describe the same kind of laws of physics, or should agree on at least something. In special relativity, that's the speed of light. In our diagram, what they both agree on is that there's no absolute sense of what up or down necessarily is. And if you want a more physical way to think of how we go from the left to the right image, imagine in the left image you're standing upright looking at the wall, but to get to the right image you're essentially got your head on the ground and you're halfway through a somersault, so you're doing a headstand. Well, you might then describe the motion of the ball according to the image or sketch on the right. But both sketches are legitimate and both are good. So now we've seen an example of a classical type of relativity. Let's move on to having a brief recap of special relativity. And as I mentioned, for this playlist, I'm presuming familiarity with special relativity. I am not presuming that you are at all an expert on special relativity. And also for those who would like a top-up or a refresher on special relativity, I've got a playlist which may be worth at points referring to as we kind of explore general relativity together. So, if we're going to talk about general relativity, it's going to be generalising a particular type of relativity called special relativity. And special relativity has all the key things that a theory of relativity would have to contain. So a theory of relativity would have to have some kind of physical principle. For example, the one that we looked at, the kind of classical notion of relativity to get us started off with, was that there's no absolute notion of what up or down is, so we are free to flip the vertical basis vectors. And essentially our transformation law was therefore just flipping the vertical basis vectors to go from one sketch on the left to the sketch on the right. And then, we talked a little bit about properties that are conserved even when we do flip the vertical basis vectors. So, we said things like the relative directions between velocity and acceleration are unchanged. And conserved quantities are very useful in physics because they allow us to say what two observers do agree on, and therefore to talk about as much of an objective reality to something as we possibly can do in physics. So let's look at special relativity and try to match it to this structure, to these three core things that any theory of relativity would have to have. So the physical principle at play, even though historically actually it's a little bit more complicated because Einstein primarily was actually interested in effects to do with electromagnetism and designing a more unified theory than the experiments actually suggested. Historically the development of special relativity didn't quite match this. But as far as we will look at special relativity today, now it's all developed, we will probably say that the core principle at play in special relativity is that non-accelerating observers agree on the speed of light. And the kind of mathematics of space-time and geometry for kind of observers' reference frames describing events of space-time when they're not accelerating was developed by people like Minkowski, by Lorentz. So we call these kind of coordinate systems that non-accelerating observers use to describe events in space-time, we call these coordinate systems Lorentzian frames, or sometimes Lorentz frames of reference. They're also called inertial frames of reference, and they're called inertial really because Newton's laws talk about kind of inertial mass, and Newton's laws are at least classically valid in an inertial reference frame. So the word inertial really comes from classical mechanics. I'll probably tend to call these frames Lorentz frames or Lorentzian frames, but you could call them inertial frames if you like. And if we were doing special relativity, I would probably call them inertial frames. But the notion of inertial is somewhat more complicated in general relativity. So that's why I tend to stick to Lorentzian or Lorentz frames. Now the things that are conserved is, well, the speed of light is the same in different reference frames, but we can generalise that idea and then say for any two Lorentzian observers, the size of any four vector is going to be the same. It doesn't matter what observer is talking about the four vector, all observers agree on the size of the four vector, even if they disagree on the components that four vector has. And the size of four velocity turns out to be related to the speed of light. But the size of four position, which is x with a kind of curly wave on top of it, the size of this four position is also something that different Lorentzian observers agree on. And the size of four position is referring to something called the space-time interval, which measures the distance between events in space-time. And if you've done a little bit of maths, kind of with vectors, at least kind of at A level and possibly beyond, you'll be familiar that the way we generally define the size of a vector, kind of generalisation, if you like, of Pythagoras' theorem, is through the scalar product, which has the symbol of just a dot. So just as the size of a four vector is preserved under Lorentzian transformation, so going from one Lorentz frame to another, similarly the scalar product between any two vectors actually is also preserved. So if we take four position and four velocity, so we do x dot with u, two Lorentzian observers will agree on what that scalar product is. Now I haven't, I think, proven that last point on my special relativity playlist, but it very naturally follows on actually from the first point. So you can kind of also think about it like if you've got two vectors on a piece of paper. So let's draw, if I can find a pen. So I've got a pen. So I'm just drawing out two vectors to show what I mean. So let's call one vector x and one vector u. I've got an angle theta. If I bring that to the camera. So here are two vectors separated at angle theta. If I now rotate my spacetime axes, which will look like I'm rotating my vectors, the direction the vectors seem to point have changed, or their components seem to have changed relative to my coordinate system, but the angle between them remains preserved. So, when we rotate our spacetime axes, or in other words, when we go from one Lorentzian frame to another, the angle between two four vectors remains preserved. And just a quick note on notation, for this playlist, and different people have different notations, I will use a curly wave on top of a vector to tell me that that capitalised letter is referring to a full vector, so a vector in space-time, whereas a vector with just an arrow over it, so like we have for velocity and acceleration on the last slide, those vectors are vectors in three-dimensional space. And so if you see a curly wave, we're talking about vectors in space-time. But anyway, so we've said that the scalar product between vectors and the scalar product of a vector with itself, so in other words, something that will refer to the size of a full vector, is conserved, and the transformation under which it's conserved is the transformation between two Lorentzian frames. This transformation is called the Lorentz transformation. Now, when we looked at it in the context of special relativity, we considered the Lorentz transformation as essentially, in its full glory, a 4x4 matrix. And because it's a matrix, there are two numbers we need to pick out elements in the matrix, because the element is going to be along a particular row and along a particular column. And so we call this matrix a rank 2 tensor. However, for general relativity, I'm not really going to be talking much about the Lorentz transformation as a matrix. I'm going to think of it as a rank 2 tensor, and we will be talking in detail about what a tensor is, why we need tensors, particularly in the context of general relativity, and how rank 2 tensors generally transform. So we won't really be representing the Lorentz transform much as a matrix, but at least in the context of special relativity, it's often very useful to do that. So to definitely begin with, you can think of it as a matrix, but it's worth saying as we go forward throughout this series, I'm trying to gently pull you away from thinking about the Lorentz transform as a matrix and guide you towards thinking of it fully as a rank 2 tensor. So we've now seen what special relativity is, and how that links with the notion of a mathematical theory of relativity more generally. But how do we take special relativity, take the structure that it gives us, and generalise it? In other words, how do we get to general relativity, some kind of generalised version of special relativity? Well, after Einstein came up with the ideas of special relativity, he wanted to find a way to be able to generalise it, to take into account non-uniform acceleration. He also wanted to unify gravity into his picture of special relativity. People were unifying other forces into special relativity. things like, quantum mechanical notions were being unified with special relativity to, allow people, for example, to look at the electromagnetic force, under cases of quantum mechanics, which was led to, quantum electrodynamics. So people were unifying forces with special relativity, and Einstein wanted to unify gravity with special relativity. But he realised, and we'll look at the equivalence principle in quite a bit of detail, in a few videos' time probably. But Einstein realised, in a way that is formally stated through the equivalence principle, that actually these two things he wanted to do, so to generalise special relativity to take into account non-uniform acceleration and generalise special relativity to take into account gravity, were actually one and the same goal. In other words, he realised that a space-time which describes how non-uniformly accelerating observers perceive events automatically has gravity encoded into it. We don't need to add gravity as a separate thing. Now those are just words, but the maths that accompanies those words and justifies it is that non-uniform acceleration through space-time implies that space-time has some kind of curvature. And it's this curvature that gives rise to the gravitational force. Or you can flip it the other way. You can say the gravitational force is described in terms of curvature, and the curvature generates non-uniform acceleration. But realistically, the link is actually a lot more tight. It's that realistically, actually, gravity and the notion of objects freely moving through a curved space-time are one and the same thing. It's not even one causes the other, it's they are the same. They are mathematically the exact same thing. And, that's at first fairly counterintuitive to say, well, a force is really just an experience of a geometry of space-time. But that's go ahead and justify it, and I've got a couple of ways of justifying it to hopefully help convince you that this idea, this equivalence between gravity and curved space-time is actually legitimate. So we've talked a little bit about relativity, what it is, what special relativity is, and I mentioned that to get general relativity, we're going to see that curvature, kind of like, well, curvature of space-time encodes gravity. But that seems like a very bold statement to make, so let's back it up with a nice thought experiment. Now, thought experiments of physicists tend to involve many mammals, and as those of you familiar with Schrodinger's cat will know, cats seem to be a popular option. Now, I'm quite terrible at drawing cats, so my cats look indistinguishable from dogs, and also I realise I haven't drawn a tail on them, so I have tailless cats. But anyway, these tailless cats are falling through a tower. Now, thankfully, I've drawn some grass and some leaves on the bottom of this tower, so they'll hit the bottom of the tower and, be able to safely plod away and will not be injured in this hypothetical thought experiment. But anyway, we have our cats, and we can ask, if we look at cat B, what does the motion of cat A and cat C look like through space-time? So what are the world lines of cat A and cat C? And we describe the position of an object using full position in space-time, and we call the change of full position, so the change of x with the curly wave over it, call that the world line. So we're asking, what does the world line of A and B look like? Sorry, what does the world line of A and C look like from the perspective of cat B? Well, cat B is in the middle of the tower, and remember, we imagine this tower to be really, really long, such that the divergence of the gravitational field is noticeable, and we can see non-uniform acceleration. So if B is in the middle, it's experiencing a medium strength of gravity, but A is at the top, so the gravitational force it experiences is really weak, and the gravitational force C is experiencing at the bottom, very close to the Earth's surface, is very strong. So A is accelerating downwards much less than B. So as time passes by, from the perspective of B, A is going to get further and further above it. Whereas for C, because C is accelerating more than B, B is going to think that cat C is getting further and further away from it, so its world line is going to diverge off the other spatial direction. And therefore we get these kind of like branching world lines, where A seems to be getting further above cat B, and cat C seems to be getting further below cat B as time progresses. Whereas for cat B, because all of this is from the perspective of cat B, cat B position isn't changing relative to itself, so its position along the space axis remains fixed, and time is just progressing, so we get that dashed vertical line for cat B. Now there's two ways to interpret this. We can either say that space-time is flat, and if we have a flat space-time, then we need to say, well, okay, these trajectories that began parallel are no longer remaining parallel. And vertically parallel lines means that the cats were initially at rest. So we can imagine that they were dropped from the heights we can see these at, with no initial velocity. But as time progresses, both cats A and C seem to accelerate relative to B, but in opposite spatial directions. However, there's another way of interpreting this. We can say that if we look at our world lines, actually these world lines are remaining as parallel as they possibly can. It's just these world lines are on a space-time that is curved. And because the space-time is curved, these world lines that begin parallel can't remain parallel, and in this case they diverge. And for any of you who have seen a curved surface, if you look at the Earth, if you've got two characters and you put them, say, at opposite sides of the globe to each other, and you get them to move, to them both be forward, so to remain parallel, they will meet at the top pole. They'll do, and get camera, they'll do something like that as they're going forwards from their perspective. So they remain as parallel as they can, but they're actually converging. So on a curved surface, parallel lines, or lines that remain as parallel as they can, will actually diverge or converge. They will not remain parallel. And that's actually a test you can do to check if a surface is parallel. And given that in general relativity we don't want to look at curved space-time from the perspective of a higher dimensional space than space-time, really we're stuck to trying to understand curvature of space-time from the perspective of the surface of space-time itself. And one of the tests we can do is look for things like trajectories in space-time that begin parallel starting to diverge or converge, as we can see here. So clearly non-uniform acceleration through space-time is the same thing as objects having a world lines that remain as parallel as they possibly can to each other, but just in a curved space-time. And because these objects have world lines that remain as parallel as they can to each other, we say that these objects are not accelerating. So, essentially, we can think of gravity as just objects not accelerating but moving through curved space-time, but when we look their motion through curved space-time through just a three-dimensional spatial lens, it looks like they are accelerating three-dimensional space. In fact, realistically, it's even deeper than that. It's curvature in space-time is mathematically identical to acceleration, or non-uniform acceleration in three-dimensional space. Now this is a kind of like thought experiment you can do with cats, but it doesn't really make much use of special relativity, and given general relativity is trying to generalise special relativity, I thought it'd be helpful to have a justification for gravity being essentially a description of space-time curvature, but starting from the perspective of special relativity, and that's what I'll do on the next bit of this video. So the next thing we've kind of got is another justification for why space-time being curved corresponds with gravity, or at least non-uniform acceleration, and this justification really builds on the ideas of Lorentz transformation developed within the special relativity playlist. So I thought it was nice to put here to really make use of some material which we've covered on this channel. So gravity is an example of non-uniform acceleration, because as we looked at with our cats, cat A is going to have a different acceleration to cat B and cat C. Now when you're doing, first introduced to gravity, all calculations with gravity tend to be close to the Earth's surface, so the discrepancy in the acceleration at which objects fall, depending on the height above the Earth's surface, is negligible, because all the things are very close to the Earth's surface. But then, as you go to A level and then you go, further, you have to start worrying about the idea that actually the gravitational field isn't uniform, and so its strength does vary, causing varying acceleration at different points in space. And we could, to understand how space-time would have to be modelled to describe this kind of non-uniform acceleration, just ask, well, if we look at special relativity, how does special relativity say we should treat non-uniform acceleration? How should we go from our reference frame to the reference frame of an observer who has some non-uniform acceleration relative to us? Well, the easiest thing to do is to just start with the observer having some kind of acceleration relative to us, and then we'll worry about the non-uniform part in a bit. So that's to say, we're looking at an observer and they have some kind of acceleration relative to us. And we're both talking about an event in space-time and give that event an associated form vector, say for position. And we want to know how to transform the components of that event from our reference frame to the components that they would measure for that form vector. Well, when we're kind of jumping from, our reference frame to the reference frame of somebody else who's moving at, say, a constant velocity relative to us, so it isn't accelerating, but it's moving relative to us at a constant velocity, we have to rotate the space-time axes. And therefore, if somebody is accelerating relative to us, we would just have to rotate the space-time axes by an amount, or by an angle that changes over time. And the angle at which we have to rotate the space-time axes is called the rapidity factor. It has a symbol phi. It's a special kind of angle because it's an angle referring to the geometry of space-time, so it's a little different to angles you may be familiar with, but it is describing the amount we have to rotate our space-time axes by. And so to summarise, because special relativity says to go from our reference frame to reference frame of an observer who's moving at a constant velocity relative to us, we just have to rotate the space-time axes. If we are going to go from our reference frame to the reference frame of someone who is accelerating relative to us, then we just have to, continuously over time rotate these space-time axes. And when you have kind of like you're smoothly rotating your space-time axes, now we're starting to talk about space-time being kind of curved in some way, because the tips of your basis vectors for space-time are now kind of following some kind of arc. So we would expect curvature to be important if we're talking about acceleration. But the thing is, if it's non-uniform acceleration, then no matter what reference frame we pick, we can't get rid of that acceleration. And to show what I mean, because I know that's a little vague, imagine we had cats, say just A and B, but let's imagine that they were accelerating close to the Earth's surface, so for all practical purposes, their accelerations were the same. Well then, if that was the case, then we could say, well, cat B isn't accelerating relative to cat A at all, so the acceleration of cat B is 0, and then we could use special relativity and not worry about curvature of space-time. We could model this just with flat space-time. However, if we have non-uniform acceleration, then as we've shown, even though cat B is accelerating, cat A will still accelerate relative to it. So because the acceleration is different for any 2 points in space-time that are separated from each other, we can never just kind of get rid of the acceleration trivially. And therefore, if we pick any point in space-time, so if we now pick a point in cat speed motion through the tower, then another point in space-time, so say where cat A is in space-time, will exhibit, it will look like cat A is moving in some kind of curved manifold, so some curved space-time. And because A will always have some acceleration relative to B, because the acceleration is non-uniform, so different places in space-time are accelerating differently. And so, with non-uniform acceleration, just using the ideas of special relativity, we would expect we're going to have to talk about space-time being curved. Now, both these 2 points used a lot of language. They haven't used much maths, but that's to give a real physical intuition for why space-time would have to be curved if we want to account for gravity by just replacing space-time and special relativity with a different kind of space-time which will automatically enforce things to move as if they were experiencing a gravitational force. So we've now kind of built up some defence from both looking at the trajectory of hypothetical cats, having a little too much fun, being perhaps a little too adventurous, to using notions in special relativity and bringing in our old friends, the Lorentz transform, which describes rotation of space-time axes when moving from one reference frame to another, to argue that gravity is completely equivalent to insisting that objects are moving in curved space-time, but without experiencing actually any additional forces, other than they would in flat space-time. It's just the space-time is curved, so to us it then ends up appearing like those objects are experiencing a strange force that we call gravity. Now that's not to say that gravity doesn't exist. Um, because, just as you could say gravity is a representation of the curvature of space-time in three-dimensional space, you could also say the curvature of space-time as a four-dimensional curved manifold is a representation of gravity in three-dimensional space combined with notions in special relativity. So it's not that we have to pick one or the other, it's just two different ways of describing the exact same thing. But it turns out, and as we'll go through this playlist, we'll see that actually it's better, it works better, particularly in cases of strong gravity, to consider gravity as being described by curved space-time. Mainly because the structure of special relativity is so neatly built up, and it's so fundamental. It's a lot easier to then just generalize special relativity than and therefore do it through curved space-time rather than keep space-time flat and somehow try to integrate gravity into that. It's just a lot more straightforward to just go down the route of curved space-time, and when you do that, you're doing general relativity, and that's what we'll be doing in this playlist. We'll be using curved space-time to describe gravitational interactions, if you like. But it's worth saying the maths we're going to be building up may be of interest to you even if you have no interest in gravitational physics, because the maths we're going to look at will involve the maths of curved surfaces, or curved manifolds, as we'll be calling these surfaces. And we'll be defining what a manifold is in a fair bit of detail, fairly soon along the timeline of this playlist. But the mass of curved surfaces is very important whenever you're dealing with geometry of curved surfaces. So, for example, if you want to make a map of the Earth, where the Earth is spherical, you want to make a two-dimensional map of the Earth, you're going to need the kind of mass we're talking about to map this 3D curved surface onto a 2D plane somehow. It's going to be imperfect, but you might be able to keep something preserved, and the mass we're going to be building will be part of that. And if you want to do any geometry on curved surfaces at all, this mass will be very useful. And we tend to call the mass of, the geometry of curved surfaces, we call it non-Euclidean geometry, because it's essentially geometry that departs from Euclid's axioms, because Euclid wrote a sequence of axioms, including the parallel axiom, the statement that parallel lines must remain parallel, which works great for flat surfaces but doesn't work well at all for curved surfaces. So we call the geometry of curved surfaces, like the geometry of a sphere or the geometry of space-time when we're dealing with gravity, we call those kinds of geometries non-Euclidean geometries. And also we'll have a look at doing maths in higher dimensions, because space-time is a four-dimensional structure, so we'll be looking at geometry in 4 dimensions. So if you're interested in extending geometry to higher dimensions, then the maths we're going to be looking at is also interesting. Definitely, if we extended geometry to 4 dimensions, there's a few quirks just associated with that in itself, which I might mention at some point during this playlist. So mathematically what we're going to be doing is fascinating in its own right, but this is ultimately a playlist from the firm stance of physics, and so we're really interested in applying the maths to physical phenomenon, or at least that's going to be my main motivation in this playlist, is to help provide a as intuitive as possible understanding of general relativity and apply it to physical phenomenon. Although if you're a mathematician and just want to see how the maths works, you are very, very welcome here too. But if you're here for the physics, some of the things we're going to be looking at is, as I mentioned, black holes, wormholes, probably white holes. And, you know, it's worth saying that although what we're going to be doing might be strange, if you looked at special relativity, you can use a lot of your knowledge of space-time to interpret diagrams in general relativity. So here we have a sketch a lot of you may have seen of a black hole. Now, one thing we're going to be looking at is how space-time changes at the event horizon of a black hole. Because without that knowledge, this diagram is misleading, but with it, it's saying something very intriguing indeed. So, if we ignore how space-time is changing at the event horizon, what looks like is happening is, you know, if we're treating the lines going towards the singularity to be lines along space, it looks like, you know, something is being pulled into a black hole, travelling almost an infinite distance in space because the black hole is stretched and at some point will reach a singularity. However, a very strange thing happens at the event horizon, and we'll look into that when we look at the Schwarzschild metric. And the strange thing that happens is the role of space and time reverse at the event horizon. So whereas the lines going towards the black hole outside of the event horizon are lines of space, when you go beyond the event horizon, so you go kind of inside the black hole, these lines start referring to time. So the diagram is showing that when you enter a black hole, you're not bound to reach the singularity because you're travelling in space. You're bound to reach the singularity because you're travelling in time. You're travelling forwards in time. Essentially, the singularity isn't a point in space anymore, it's a point in time in the infinite future. And as time progresses, the space around you, marked by the kind of like circumference of the circular rings, which within the black hole represent space now, those contract. So if you were falling to a black hole, what would you would notice that you were being in some kind of free fall. You wouldn't experience much forces, and for you it wouldn't look like you're falling down to a singularity. You would just see the space around you contract and contract and contract, and at a point in time that seems to at least people outside of the black hole to be an infinite amount of time into the future, the space-time around you shrinks to zero volume. Now quantum mechanics says something funny might go on before a singularity is formed. I probably won't be talking much about ideas of how quantum mechanics comes into general relativity on this playlist. I might do, but that is so cutting edge. I'll see if I can find a way to make it intuitive, because I want everything on this channel to be at least partially intuitive. I don't want to just rely on the maths. Then I will. But I'll see if I can find good physical intuition for quantum-led gravitational effects. But anyway, so that's kind of like where we'll be going on this channel, to look at kind of general relativity and all that jazz. And now just a quick mention for useful resources if you're interested in learning about general relativity further along with this playlist. If you would like to just skip this part and move on to the next video on what will become a playlist on general relativity, cool, and you won't be missing any content. But it's worth saying for those who would like some extra resources, there's a few I would recommend. So I'm just going to quickly get the books and I'll be back in a moment. So So, for those of you who would like a nice kind of introduction to general relativity, you know, and some, of the background maths introduced before it gets going, I would recommend this book, and I'll put a link down in the description. But it's a most incomprehensible thing. Well, that's its title. The book is not incomprehensible. I think it's kind of a slight joke, really, the title. At least, Einstein's ideas seem incomprehensible, but as we'll hopefully show through the playlist, there's a very comprehensible, if still headache-inducing, but definitely, I think, comprehensible route to take to general relativity. So, this book is really good. It's written by someone who I think their original degree was an engineer. So, it's very practically driven. And written by someone who at least initially, I think, didn't do, physics at university. So, it's written really for the non-physicist, but it's great, even if you have done physics as well. Although if you've done physics, you can probably skip through a fair bit of stuff on special relativity. But if you want something a lot more rigorous, particularly if you're more mathematically inclined, I would recommend this book, so Spacetime in Geometry by Carroll. This book, it's worth saying, is I think mainly written for postgraduates doing theoretical physics. So if you're a late undergraduate, so like in your final years of undergraduate maths, this book will probably be good, and if you're doing postgraduate physics, this book may be helpful as well. It's worth saying I will be using this book in parts for some to look over some stuff. It is incredibly mathematically dense at points. It's clearly written to partially cater to pure mathematicians as well as to physicists. So, that's worth bearing in mind. Nonetheless, it is pretty comprehensive and is a really good book. There's also a playlist, MIT playlist. I would really recommend MIT open, courseware stuff, free YouTube videos, also perfectly legal, on YouTube, because MIT freely share their resources. Well, some of their resources anyway, by which I mean some of their lecture courses. And I think it works great for MIT because they're brilliant courses. But I would really recommend that course, at least in the initial parts. It's worth saying because the board is viewed from a fairly distant camera at points. It's sometimes very hard to read what group symbol is being written, particularly when you get to the point of curvature and dealing with curve manifolds, where there are a lot of Greek symbols and subscripts and superscripts, and they're distinguishing between the alphas and the betas and the gammas become a little difficult. And the order of symbols is very important in general relativity, so that that's a disadvantage of viewing that course on YouTube. However, the benefit of that course is it tries to be very intuitive as well. It's a lot more formal than what I'm doing, but there are benefits to that as well. It really does cut to the point very quickly. So those are my main suggestions. I'll put links to all of those down below, but there's a lot of really good books out there. The only thing I would say to be careful of is if you do want to buy a book to learn general relativity, make sure it covers general relativity properly. So has at least half the book devoted to general relativity, because there are some books which will say they're going to talk about general relativity, and they do, but they only have like a couple of chapters on it, and most of the book is on the development of special relativity. So if you want to learn general relativity, make sure the book covers it. Have a look, if you can, at the index, or just look through the chapter titles to make sure a good amount of general relativity is covered. But anyway, I hope you've got something out of this video. I hope it's excited you about the oncoming playlist, and I look forward to sharing more wonderful general relativity with you hopefully soon.